Guess it could be worse. Welcome. I have no idea why I did that. Any other questions on homework or general stuff? Anyone feel like they should get a t-shirt? It's for getting to the 5th. Every week you should have gotten a shirt. I made it to the 5th week. It's the 5th week, people. What's next week? What is next week? What happens next week?
We die.
The final.
Man,
No.
that was rough, man. Did you say we die? Oh, man. Yeah, everybody. We die, so it's time to party. No, stop. No, so next week is the final. I actually do have a practice final that I will unlock at some point for you guys. Right? So next week is also, obviously, the last week of class is next week. Holy shit! Feels like we just started. Or, I don't know, some of you guys are like, it feels like it's been 80 years, Jeff. Okay, I'll try not to take that personal. Looking at your face for 80 years, boy. All right. No other questions from, that's a little surprising. No other questions from anything? There's some really good stuff in office hours. Okay. I'm cool with it. Let's see. Let me see. I unlocked a couple things in Canvas. Let me show you real quick. Oh yeah, we do. I forgot about that. All right, hold on. How did I forget that? We still have to finish up chapter 8. Yeah, buddy. So I'm gonna unlock this right now. This is good. Oh man, this is gonna be so exciting. Okay, so that's where we'll start. So if you go into chapter 8, oh, you're gonna love this. You're gonna click this and you're gonna say, that looks exactly like what I wanted to see, Jeff. More numbers on a sheet of paper. I love it. Kicks so much ass. What the shit does this mean? We're gonna talk about it. We're gonna talk about it. Okay. First thing is I gotta explain what the hell this is in general. So I don't know if you guys remember, last time we were together, I told you that well, let me just tell it to you, because now I can't even remember if I told you this. What is it that? All right, let me write some stuff up on the board, just to get us all in the same place. Hopefully. Yeah. All right, get in there. Ah. Oh my God, I gotta clean you. You're just a mess. All right. Now, I kind of made a point of this when we have this formula. There was a part of it that didn't necessarily always make sense. So it makes sense that we don't always know the population mean, right? We don't go into a situation suddenly knowing the entire population mean. That doesn't happen very often, right? That would be like the statistic psychic. That would be so neat. Walk to him like, the mean is 7. What? All right. The other thing that's kind of weird, and I showed you an example of why this isn't as weird as it could be. What is all that crap? Get out. This here. We also often don't know sigma. Somebody remind me, what the hell does sigma mean again? What's it stand for?
Standard deviation?
Of?
The population?
Population? That's right.
I wasn't sure.
That's okay. So I want you to understand. I gave you an example where a situation where it made sense that we knew this, but we didn't know this for a specific group, right? So maybe we know the population standard deviation, but we don't know the mean of a group over here or something. So there are situations where it makes sense that I somehow know this. Most situations that statisticians deal with is they walk into a new situation, brand new data, don't know shit. So I take a sample, I could find this from a sample, correct? I can find that from a sample. I cannot find this from a sample. What do I do if I don't know this? What can I use instead? What do I have to use instead?
The data points.
What about the data? Well, so remind me. All right, is everybody cool with this? If I don't know the population mean, can't I just use the sample mean?
Yeah.
Yes, and the whole point of this was to improve on the sample mean because it's probably not the same as the population mean. That's the whole point of a confidence interval, is to kind of improve on our guess. Are you guys semi with me? Anybody? Give me a thumbs up or a thumbs down. Give me a frowny face. Give me a reaction of some kind. Give me a party symbol if all is good. Or if you don't care anymore and you're like, I'm just drinking and watching you do shit, Jeff. No? Okay. Now, stay with me. I really want this to make sense. It has to make some sense. If I don't know what is going on, I think I'm my barber, by the way. If I don't know the population stuff, the next best thing I've got is the sample stuff. So if I don't know sigma, we must use S. What's S?
Sample standard deviation.
Standard deviation. There you go. Cool. I like it. Now, stay with me. Is S the same as sigma? How much money would you put on some sample we took having a standard deviation that's equal to the actual standard deviation? How much money would you put on that?
How big is the sample?
I don't care. That's a good point, though. I love it. That actually is going to feed into this thing. So whoever just said that, you have a special place in my heart. Let's say it's 100.
I think it would be off.
Yeah, I would put a lot of money on it being off. If there was an option, I would put a shitload of money on it being different. You with me? Anybody? I take a sample and I find a standard deviation of that sample. I am as certain as I can be that that will not be equal to the standard deviation of the whole population. Holy shit, does that make any sense to anybody? If that happened, I would write a paper. I would call a friend. Yes, and I have friends who would be interested to hear that. Hey, guess what? My S equals sigma. What the shit? Yeah, man, take a shot. Oh yeah, that's right. It's a game. You don't get very drunk off that game because it hardly ever happens. So now watch this. So I'm gonna use the same formula except I'm gonna leave that blank for right now. What did we just say? This is almost certainly wrong. You with me? So let me ask you, all right. This is so funny that so many of my examples deal with fish, but because they don't like fish. Anybody out there like to eat fish? Anybody out there like to fish? Anybody out there know what fish is? What's happening out there? These things that swim in the ocean? That's not real, Jeff. They're not real. All right. So let's say that you're going to throw a net out. And I think of a fish net as my confidence interval. I think I've used this before. So if I want to be more confident that I catch a certain fish, wouldn't I throw a larger net out? That's related to the confidence interval getting bigger, to be more confident. Are you guys semi with me? Oh yeah, don't be careful about pescatarian, Presbyterian. Right? One requires baptism and the other one, I don't know. Maybe they do. I don't know what pescatarians do. Now, stay with me. If you had no idea, okay, the concept of fish, exactly. If I had no idea how wide the swimming path was for a fish, wouldn't I have to make my net even a little bigger to cover for that? Okay, so here, if I knew this, I know exactly how much variation there is in where the fish is. So I can kind of set my interval at predefined. But if I use this, I got to cover my ass more. I've got to make a larger interval to make up for the fact that this isn't right. So what is S doing for us? It's an estimate for this. Are they equal? No. So in every instance of any interval we've made so far, if I didn't know sigma and I had to use S, I would want a bigger number here. Wouldn't that make the interval bigger? So I really want this to make sense. If I use S, I need my interval to be bigger than normal to cover my ass for not knowing something. So I need to use a number that's kind of like a z-score, but isn't a z-score. It's always a little bigger. And that's actually called a t-score. And how much bigger it is depends on how big the sample is. The bigger the sample, the smaller t can be until it becomes the same as this. Because the bigger the sample, the less I need my ass covered, because the more certain I am about what I see, related to the question somebody had about how big was the sample I was talking about. So any chart that deals with finding this has to be dependent on the sample size. The smaller the sample, the bigger this thing's going to be to cover my ass more and more. All right, I have no idea. Side note, just a little side note, historical thing. The t-score was invented by somebody named William Gossett while he was working at the Guinness Brewery. Brewery. Anybody drink Guinness? Anybody ever heard of Guinness? Yes. I don't personally prefer Guinness, but I drank it with my physics professor in grad school because you just wanted to get in with your teachers. So I'm like, you're drinking Guinness? How's Guinness? Anyway, so grad school's a whole different world of kids. Let me think. Where was I? All right, so this guy Guinness, he did a lot of research on stuff related to brewing the Guinness, and he wanted to put it in an article, but he wasn't allowed to have that research for himself because the company would take it. So he published it under a pseudonym, under a fake name. He called himself Student. So this is called the Student's Tea Distribution, right? Based on research in Guinness. So let's take a look at this weird freaking chart. Get over there. Oh. Before we do, does somebody remember the discussion we had? Remember when we did this formula? Yeah. Does anybody remember what this formula was for? You guys can see it? I don't know. Anybody? Does that formula look at all familiar?
Yes, but I forgot what it was for.
Was that the variance?
Good. For a sample. And remember, for a population, this was n like it's supposed to be, right? Sum them up, divide by how many there are. Do you guys remember me talking about n minus 1? That if I had 3 things, I could just totally make up 2 of them, but I had to be careful about the last one, so I have n minus 1 degrees of freedom. So degrees of freedom is just N minus 1. So if I had a sample of 11, what's my degrees of freedom?
10.
10. Crazy. Holy shit. All right. So with all that knowledge in mind, let's take a look. Let me show you guys in case somebody came in later. Here's the t-score chart. You can access this on the canvas in the unit 8. There it is, t-score chart. Now, I want you to notice a few things. Okay. This is set up so weird. Does anything look familiar? Immediately familiar? Anything?
It's like a z-score chart.
Okay, looks like a z-score chart, sort of, right? Sort of. Look at the very bottom of the chart. Does anything look familiar down there?
Those are the critical values?
Yeah, don't they look familiar? 1.96, 1.645, yes. Even 2.33, we might have gotten that once or twice. 2.575, this is actually a little more accurate. 2.576, just a little more accurate. That's weird. What's this column here?
Freedom.
Degrees of freedom. So this is related to how big the sample is. I really want this to make all the sense in the world. When is it that I am less certain about what I've discovered? When I have a big sample or a small sample?
Small sample.
Small sample. So the smaller the sample size gets, do you see what happens to the t-scores? They always get what?
Bigger.
Bigger, because they got to cover your ass more. I really want that part to make so much sense. That actually is not really different at all from the mathematical concept, believe it or not. Me saying it's got to cover your ass more is basically exactly the mathematical concept. If I take a smaller sample, I am less certain about the spread. I've got to cover my ass more for that reason. So my interval gets a little bigger and bigger. And look, if I have a sample, what sample size would this be? The very first row. What sample size would that be?
2.
2, good, because that's n minus 1, so it's got to be n is 2. So I have a sample of 2. Look how big the t-score could get, which makes sense. If you only take 2, you don't know shit, right? If you're like, oh man, what percentage of Americans would vote? And let me take 2 people. Screw you. That's not going to tell you anything. Are you with me? That's why this goes so insane. Now, so let's break this down further. So we see how this relates to the idea that as my sample size gets bigger, I need my t-score. I don't need it to be as big anymore because I'm more and more and more certain about what I see. Does that make sense by itself? Maybe. Okay, the 3 people I can see are nodding yes, so I'm going to keep going. What the shit's going on up here? I've used this word before, tail. What does that have to do with? Like, if I make a confidence interval, how many tails did I just make?
2?
2. And let's say I want to be 99% confident. Can somebody tell me how much is out here?
0.05.
All right, on either side would be 0.005, right? But if I was 99% confident, isn't there, so there's 0.005 in one tail. You with me? Really want you with me here. And there would also be 1% in 2 tails. Does that make sense? If there's 99% in here, there must be 1% total in 2 tails. Do you see how either way you look at it, you're in the same column? Isn't that nice? This is math people trying to be nice. We do try that every now and again. Now, to be really honest, we're going to see the full reason for this in chapter 9, because we will have hypotheses that could lead to a 1-tail or a 2-tail test. And then I know exactly where to look. All right, maybe. So let's try this. if back in the day, all right, let me erase this here. You guys ready? I'm going to clear this away. Go away. Can somebody tell me if I wanted to make a 95% confidence interval, and I was going to use a z-score because it's normal, and I know sigma and all that kind of shit, right? Could somebody look up what would the z-score be that I would use for 95% confidence interval? You guys, somebody even remember that? No?
Like 1.62.
1.96? Does that sound familiar?
1.96.
Yes. And in fact, all right, so now watch. So two things I want to show you. 95% confidence. Which column does that relate to? Do you guys understand what to think about now to see which column it relates to? If it's 95% in, how much is in two tails? How much is out total?
0.05.
So 5% in two tails, right? So I'm in this column. What do you see at the very bottom of that column? So where it says large is where they are just z-scores. Because when I have a large sample, I don't need to cover my ass more. Then I'm confident enough about it. And I love this. Anybody wondering what large means? Anybody? What it means is this. You ready? It means it's large. So it depends on the situation, to be honest, right? But in this context, you can take it to mean anything above 2000 if you want to be that literal. And look how close these already are anyway. Do you guys see that? They're almost these values. So yeah, it basically means anything over 2000 for us. Okay, stay with me, stay with me. I love it. Now, coming back up here. What if I realized, oh shit, I don't know sigma. I can't use z, but I do know it's normal. That's important. I only know s. Oops, what's happened? Yes, I agree, Jessica. Very good point. Should be labeled large enough, which would still be like, what does that mean? Whatever it means to you. It's very philosophical. Take away from it whatever you bring. Bullshit. Oh, sorry. So what if I only know S and my sample size was 14? Can somebody tell me what my degrees of freedom would be?
13.
13. That's the easy step. So now I know where to stop, right? I stop at 13. And I still want a 95%, which is still this column. Is everybody with me? So now I know I go down until I get to 13. So I would use, instead of 1.96 in the formula, I would just put a 2.16 there instead. Are you guys understanding that this barely does anything to the work that I need to do? Don't worry, we have.
How did you get 13?
Oh, remember, degrees of freedom is always n minus 1, and if n is 14, that's got to be 13. Yeah. So a really good question from you guys would be, why the shit didn't they just make this n and make this 2, 3, Jeff? Because degrees of freedom is a really huge idea that gets more and more important the further you go in statistics. So they really just want to start putting that and making you think about it now. All right, so let me take this to it. Now, all right. Let me give you one more thing while we're looking at this together. What if I want to be 98% confident? I don't know sigma, but I know S, and N is 23. What would the t-score be? Don't say anything yet. Don't say anything yet. Try to figure out. So let me ask you one piece at a time. Which column, 1, 2, 3, 4, 5, which column are you looking at?
The second one?
Second one, good. Because 98% confident means 2% in two tails. So if I have a confidence interval, I pretty much always look at this row. Because it's always a two tail. It always cuts it, makes two tails. Because it's the middle, chop, and it's got two tails on the outside. All right. And then I want to stop where? What's the other? Do I stop at 23? Where do I stop?
22.
Stop at 22 because that's the degrees of freedom. Degrees of freedom is 22. So my t-score would be 2.508. That's what I would throw into the same spot Z used to hold. I really want you to understand. Yes, I understand. Part of you like, another freaking chart. Shit. I don't understand how to read the shit. But once this chart's not hard. It's just new. And it's just another number to put where Z normally goes. Now, what's important also is that I really hope you understand why this makes sense. And again, it really just comes down to covering my ass when I don't know the population standard deviation. That's what it really comes down to. I don't know how you feel. All right. So, oh, there's a chat. Let's see what's going on. Oh, I love it. Don't worry, we're gonna get that. We're gonna get that in a minute. Okay, let me do this. I'm gonna shut this down. You guys ready?
Are the charts going to be available during the quizzes?
You can print them out. To be honest, so today's quiz, I think at one point I thought about throwing the Z-score chart on there, but at this point, you guys need to have the Z-score chart accessible, right? Is that not true for somebody? Yeah, you can pull it up on the computer. That's fine. You should. If you don't have a printer, I'm not going to try to printer shame you. It's okay. You don't need to have a printer, but you can certainly access it on your computer, as long as you're not accessing Google or Chegg or anything. Cheat at math homework on Reddit. None of that shit. Right? Okay. All right. So I'm going to close this down. And then we're going to look at this. I know you guys are not going to believe this, but I have a worksheet. Let's see. If you really hate worksheets, you really hate me. So it's right below the T-score chart. It's called T-score practice right there. All right. So let me open this a different way. Can you guys all find that? I'm going to open it a different way. Don't freak out. Ah, Jeff. All right, hold on. All right, let's see. Oh, I never remember to do this ahead of time. Shit. Let's see. Here we go. Math 160. What is it? T-score practice. Where are you? Well, there's the answers. Where's the? That's good, Jeff. The answers. I need the sheet. Just download it. It's gonna be all right. Okay. There we go. All right, where is it? Oh, yeah. All right, let's take a look at this thing. I got to open my T-score chart too, but let me try to do that. All right, so take a look. So I call this one lightning round at the top because it's just, by the way, let me say this before we get into that. Can somebody tell me very concisely why were T-scores invented? I don't need a whole history lesson. Just tell me basically why were T-scores invented for what situation? What was the whole point of everything for when I don't know what?
The standard deviation for the population?
Thank you. Yes. I was going to say which, but you kept going, and I'm happy. When I only know the sample spread, the sample standard deviation, and I don't know the population one, that's why T-scores were invented. You guys with me yet at all? A little bit? That is why they were invented. So when you say, when am I supposed to use t-scores? Well, that tells you when. You know why they were invented. So you have to use t-scores when you only know S, when you don't know sigma. So let's take a look at this again. So t-score lightning round, find the t-scores, assume a normal distribution. So it's got to be normal to use Z or T. It's got to be normal. And I only know S. I don't know sigma. So try to do these, and I think this part will answer somebody else's question from a minute ago. Try to do the first two. I'm going to continue to try to find my t-score chart. Where are you? T-score chart. Where the shit are you? There you are. Yay! No, I don't want that. Okay. Hopefully everybody's doing something. We're doing this first problem here. Oh yeah, shoot. Oh, that's right. All right, let's do this real quick. What's the degrees of freedom for part A?
5.
5. And somebody else for part B?
100.
And somebody else for part D? I'm sorry, C?
92.
92. I like it. Now, so degrees of freedom, easy as shit. No, I'm sorry, easy as anything. There's little tiny ears out there. I want to be so going back to part A, I want to be 99% confident. So which column am I looking in? 99%.
The first
First
one.
one.
First column, I like it because that's got 1% in two tails. Is there anybody that's not understanding what we just said? You can privately chat me if you don't want to out yourself. Okay. I'm going to assume everything's good. All right. So I know which column, and here's the thing, are you ready? If I stop somewhere, I get a t-score. If I go all the way to the bottom, I get a z-score. So guess what I'm going to do later today? I'm going to look for a z-score on the t-score chart. Of course I am, because they live here at the bottom. Oh, who lives at the bottom of the sun? So I'm going to go in this column, and I'm going to stop at 5, right, for the first problem? Because the degrees of freedom was 5, so it's 4.032. And I would just put that in to the formula. I would just put it here. Just like I would put a z-score there. So nothing really changes. I just have to get the number from a different chart. What I do with it doesn't change. Does somebody got part B? Which column would I look in?
Third one. Oh no, the fourth one.
Fourth one, I like it. So 90% means 10% out and two tails. And then where would I stop?
A 100.
Yeah, stop at 100. So you get 1.660. You guys see that? So instead of 1.645, a number that we've seen several times, I would use 1.660. All right, now, does somebody think they figured out this one? Which column am I looking in?
The second column.
Good, because I want 2% in outside, right? In two tails. The problem is, where do I stop? Is there a 92?
I think you stop at 90.
Good. I'll stop. That's creepy. That's very good. Now, the thing is, what happens so often in statistics is you penalize yourself for not knowing something. Which one makes the t-score bigger? If I go to 100 or if I go to 90? 90. That's the one I use. I penalize myself by making the number I use bigger. Make my error bigger. You guys with me? Now, if your degrees of freedom was 99 and you use the one for 100, that's fine. Does that make any sense? I'm not going to be like so strict on this, because guess what normally happens if you're in a job that requires you to do z-scores? You're going to use, c-scores. You're going to use software. You're going to use some program to do all the shit for you. Now, you still have to know enough stuff to interpret it and to program it. Yes. But it's going to get the exact t-score. So Jeff doing this weird ass thing where I use this chart, instead of letting you use all the buttons in your calculator, is the calculator more correct? Yes. Do I give a shit? No, not the first shit is given, because this is all about learning. I want you to see how the t-scores change as you move up and down this thing. I don't care that we don't get the exact right t-score. That's for later. We're not building bridges right now. Nobody's going to die because our t-score was a little wrong. Once you're out in the real world, then your job can hinge on the 15th decimal place of your t-score, not here. All right, I'll stop with that shit, sorry. So coming back to this, I forgot what it was because I talked too much. 2.368? Is that what it was? I think so, right? So it's here, here, yeah. And then stop at 90, 2.368. Okay. So my very bad joke, there ain't no party like a z-score party, because a z-score party don't stop. So if you stop, you get a t-score. If you don't stop, you get a z-score. Okay. So this is the ultimate baby chart. Remember the baby chart on the z-score chart? For like 90, 95, 99%. Well, this is even better. This has my third decimal place, and it's got 98, and it's got 80% confidence. It's got more shit on it. Yay. So you can use this for z-scores. All right. Sorry. Really, this is too much for a Monday, Jeff. I'm sorry. It's just what you signed up for. So look at 2.
Question.
Yes.
So the t-score chart, the area in two tails, it only goes up to 0.20. Would we never get a majority percentage more than what would need 0.20? Does that make sense?
80. Now think about 80% confidence.
Uh-huh.
What's the probability that you're wrong?
It's pretty high.
So you would hardly ever see an 80% confidence.
Okay.
There
So you
are
only need it
other-
up until 0.2.
Huh? Sorry?
So you only need it up until 0.2.
Definitely, even that's crazy. But there are other reasons this is here. It's not unheard of to use an 80% confidence interval, but that would be a really strange situation, and they happen. But there's other reasons this does this, which we'll go into the more shit we learn. So we'll come back. This is going to be used a lot for the rest of the semester, just so you understand. Because in statistics, how often do you think it is that we know a population anything? Population mean, population standard deviation? Not often. So the minute we don't know this population standard deviation, we got to use this shit. All right, I'm a little amped up. Why am I amped up? I was tired this morning. I don't know. All right. So let's look at this sequence here. Can somebody, do you guys know, if I ask you, which one of these situations we cannot do anything? Can somebody look through and figure out, don't say anything yet. Can you look through and figure out A, B, C, or D? One of them we are unable to do anything with. What situation is it that I can't do anything?
C.
Sorry?
I said C
All right, why do you think C?
because it's not greater than 5. But I could be wrong. The way that I'm thinking about it.
You're looking at it the wrong right way. I don't know. Yeah. You're thinking about NP got to be greater than or equal to 5.
Yeah, that's how I was looking at it.
So look, is the population normal to start with?
No,
Does the sample size save it?
no.
No, because n is supposed to be greater than
30.
30. There it is, right? So C is can't be done. CBN, Jeff, what are you thinking about? CBD, THC, no, get out of there. So, right, so C I can't, see, I was trying to see who knew, but so C I can't do. Does that make sense to everybody? You guys with me? If it doesn't say it's normal, what's going to save its ass? Sample size. Oh, this poor little dude wasn't saved. So kill him. Die. So I can't do it. Now, why are all the other ones good? Why is A okay? N's only 22.
Because the population is normal.
It's normal. So that's okay. I can do something, right? Why is B okay? It says it's not normal.
It's greater.
Greater than 30. I love it. And why is D okay? D's like the best. He's like chilling. He's fine. He's like, I'm normal and my sample size is bigger than 30. I'm all good. All right. Now, let's go back. So is everybody with me about which one I cannot do, why, and the other 3 are good? They have to be normal to do anything. Now, can somebody remind me, what tells me when I can't use a z-score, when I must use a t-score? What is it that tells me that? Why were t-scores invented?
If you don't know the standard deviation for the population.
Yes, so look at A, B, and D. Look at A. Do I know the population standard deviation?
Yes.
Check, so I can use z-scores. Can you take a minute and figure out what the 90% confidence z-score would be? And it'd be really great if you use your t-score chart to do it, right? So 90% confidence. Which column am I looking at?
The 4th one at the very
Fourth one.
bottom.
And I just don't stop. Yeah, good. So 1.645. That would be the z-score I would use. Oh. Oh, all right. Somebody's asked me about the 1 or 2 tail thing. The one, so right now, all that 1 tail means to me, if I have like a 90% confidence interval, how much total is outside? There's 90% inside. How much is out in 2 tails?
10%.
10%. No, again, I said how much total is out? 10% total in 2 tails. 10%, 2 tails. How much is in 1 tail then? Like my man said, 5%. Isn't that the same column? 5% 1 tail is the same as 10% in 2 tails, yes?
When would we only need to use 1 tail?
In chapter 9. In chapter 9, we're going to have stuff like, let me see if I can throw this at you. Somebody says, I think the average age is 40, and somebody else says, I think it's more than 40. This would be a 1 tail test. The only way that the one guy who thinks it's more can be right is if the sample is up there. That would be a 1 tail test. Now, if that doesn't make any sense, we're not in chapter 9 yet, but chapter 9 is where we will use 1 tail and 2 tail independently. You guys with me? Okay. Don't worry. This is weird shit. This is brand new. I can't talk about everything because part of what we do with this is in chapter 9, and I have to teach you chapter 9 first. So I can't tell you all that yet. All right, let's come back. So what about part B? What score? Can I use a z-score? Do I have to use a t-score?
T-score,
Why t?
because you're given the standard deviation of the sample and not the population.
I don't know sigma. I don't know the population one, so I'm forced to use a t-score. Right, that's my punishment. I kind of hate saying it like that, but at the same time, it's basically what it is. We don't know something, we got to be punished for it. You guys are going to be reporting me. You was talking about punishing me? I don't know. All right, so now I want to find the t-score. What do I have to know before I can look it up in the chart?
Degrees of freedom.
Yes. And what are the degrees of freedom?
38.
Good. Just remind everybody. That's all you got to do. Take one away. I like it. And 98% confident. Let me tell you this. I always forget about these little things. Let me plant this. Oh boy, you guys are going to love this. Stay with me. This is going to become very important much sooner than you think. You already know this. So 98% inside means how much is in the two tails. So
0.01. Oh, 0.02.
102. All right, now watch. I'm going to introduce a new symbol. Why not? Why not, Jeff? You introduce a new chart. You're talking about freaking Guinness and shit. Why not just give us a new symbol? So here's the new symbol. It's a little fish. Right? Does anyone know what that actually is? What letter that is? Greek letter. Alpha? Yeah. So alpha is the area in the tail or tails. That's all it is. Alpha is the Greek letter for what? What's it relate to? Kind of is a giveaway. What letter in our alphabet does it relate to? Anybody? Alpha.
A.
A. So A for area. So little fish dude. What do fish have? Tails. And what is alpha? It's A. So what does alpha mean? The area in the tail or tails. That's what the letter alpha means. It's the area in the tail or tails. So alpha is 0.02. Isn't that what we actually look up on the t-score chart? 0.02. And then where do I stop again?
38.
Where am I? Here we go. Stop at 38. There it is. 2.429.
Can you explain how you didn't remember or letter A?
Sorry?
Letter A, how did you get 1.645?
No, that's the z-score for the last problem.
So did you just
So all this is, see how this says 98% confidence? Yes.
yeah.
What's the area in the tails? If there's 98% in here, what's the area in the tails?
Oh no, I understand this problem, but can you explain how you did letter A?
Oh, okay, so you said alpha. Okay. All we did there was, all right, 90% confidence, which means how much is in the tails?
Okay.
90%, yeah, 10%, right? 10%. So alpha would be 0.10. So when I look at here, I go to 0.10 in two tails, right?
Mm-hmm.
Now, was it a t-score or a z? It was a z-score, right?
Yeah.
So I don't stop. If I stop, I get a t-score. If I don't stop, I get a z-score.
Oh, okay.
Why? Because the bigger the sample, the more certain I am about what I get, the less I need a t-score to cover my ass. So in the event that my sample is freaking huge, I don't need t-scores. I can just go ahead and use z-scores. That's why there are z-scores on this chart. Now, I know, has anyone ever seen Abbott and Costello? All right, it's funny. Some of my older students have, I myself am older, so I'm okay with it. But Abbott and Costello I just feel like sometimes as I'm teaching, I'm thinking this sounds like a script for an Abbott and Costello routine. Maybe I'll show you one eventually, because everybody should know about Abbott and Costello. It kind of makes me sad that some of you guys don't know. All right, so we said part C, we could not be done, right?
Real quick, so whenever we are given the standard deviation of the population, so like in A, we will always have the last, you don't actually use the z-scores chart, you just use the z-score given in the t-score chart, the very bottom bar.
Yeah, and I want you to realize this is a very specific chunk of the z-score chart. I mean, it's just, these are z-scores down here. So all a t-score is a slightly bigger version of a z-score. And it gets bigger and bigger as your sample gets smaller and smaller. So the other way around, it gets smaller and smaller and approaches a z-score, the bigger my sample gets. Okay. I love it. You guys out there are like, I was wondering how this class could get any worse. And then today came. Now, what about this last dude? Z or T? Zort. Z or T?
T-score?
Say again?
The T,
T. Yes. Why T?
because we don't know the, we don't know the standard deviation.
Of the population. We only know the standard deviation of the sample. I like it. So then what's my degrees of freedom?
60.
60, right? It's one less than the sample size. And what's alpha?
Point oh one.
1. I love it. If there's 99% inside, there's 1% in the tails. That is what alpha means, the area in the tail or tails. So now I know I'm going to look in the 0.01 column and I'm going to stop at 60. So I'm going to look in the 0.01 column and I'm going to stop at 60. 2.660. Of course, it always tickles me that there's a 1.660 and there's a 2.660. All right, sorry. I'm a math guy, so numbers. Jimmy, go.
So the t-score for letter B, did you just write it real small? Is it
I
the
did.
2.429?
Yeah.
Oh, okay.
I talked about it and I realized later that I didn't write it down. See, there it is. 2.429. I just never wrote it down. Now listen. Have we done a confidence interval t-score problem yet? No. All of this is just getting used to when do I use t-scores versus z-scores and how do I find them, right? That's all this has been. So here we go. Number 3, finally. Something with a little teeth to it. Get out of there. Oh, you're going to love this shit. So now that we can do a problem when we only know S, you're going to see problems like this. So why is it okay for me to do anything on this problem? Why can I do something? What do I look at to see if I can do something?
Because it's normal.
Good. It comes from a normal distribution. So it doesn't matter, there's only 7 grades, correct? It's already normal at the beginning. To find a 98%, I put the formula here. To find the 98% confidence interval, I need to know X bar, I need to know S, I need to know N, I need to know T. How am I going to find X bar and S? Well, I basically tell you. What do you have to do? Put it in your list, use one bar stats, right? So go ahead and do it. I'll do it with you. So put that data into your list. We haven't had to do this for a little while. Oh, let's see, did I put them in there right? 65, 78, 55, 98, 94, 87, yes. All right. All right, all right, all right. What'd you guys get? Or I'm sorry, you still doing it? Anybody get something yet?
Yeah,
No?
for the sample mean, I got 78.2857.
All right, we'll say 286. And then how about somebody else tell me, did you get a standard deviation? Is anybody not concerned, but is anybody like, well, Jeff, I always know sigma, math boy, because my calculator, oh crap, there we go. My calculator tells me sigma, math boy. Ha, ha, ha. Is my screen stuck? Or what do you guys see? I don't know. Can you guys see that? It always shows me S and
Yeah.
sigma, right? It always does. It always does. Where am I at? There I am. It's dumb. This is dumb. I just want to clip that piece. This is dumb. This is dumb. This is literally stupid, right? It doesn't know that the numbers I just put in, if they're a sample or if they're a population, it doesn't. That's not its job. It doesn't have to know stuff like that. We're the humans. What did we put in? We put a sample. So which one do I have to use? I have to freaking use S. I can't choose to use sigma. It's not a population, right? This is a sample. Calculator doesn't know that. It's stupid, right? I'm sorry. Don't mess up now. Oh man, I shouldn't talk down to my technology because it's gonna mess with me later. All right, so what did we get for S now? 15.724. Is that cool, guys? You guys okay out there? Okay. And now just plug and chuck. I'll wait. Go ahead and plug it on in the equation, and I'll sit here and wait. Do, 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 do. Do, 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 do. All right, let me catch up to you guys a little bit. So this will be 78.286, give or take. No, Jeff, you crazy. Oh, we haven't looked up the t-score yet. Did you guys look up the t-score? Here, let's do this real quick. What's alpha and what's the degrees of freedom? What's alpha?
0.02.
Good. 98%, so 2% outside. And somebody else, what's the degrees of freedom?
6.
6. Good, because it's 7 minus 1. That's crazy. So then what do we get for the t-score? 0.02. Stop at 6. I get an approximation for pi. That's awesome. 3.143. Not the best approximation, but it's passable. One really big mistake I see people make is they'll put a 6 here instead of a 7, right? But the formula needs an n, not an n minus 1. You guys doing okay out there? I can only see 3 of you, so I have no idea how everybody else is doing.
So how did you find X bar using the calculator and the
1 var stats, remember 1 var stats? You just put them into list 1, you can do 1 var stats. Do you remember that? No?
so I put it in the list, but I don't know what to do from there.
Whoa, wait a minute. All right, here we go. All right, hold on. I got to do my little Zoom thing. All right, let's see. Hold on. All right, so then you would go to calc. Okay, I can't do this. Go to calc. See the first thing, 1 var stats? You want to do it on L1. What does mine say? L1, okay. Is that all right?
Yeah, thank you.
Sure. Oops. All right, let me see. Hold on. Oh, there I am. Okay. Coming back to this. Did anybody get the error yet? Error. Now, obviously, if you didn't understand confidence intervals, this is going to make even less sense. But if you understood confidence intervals, this is the same thing. I just put a different number right here than I normally would, right? That's it. That's the only difference. And I really want the concept to make sense. I want to push my boundaries out. I got to catch more shit because there's something I'm not sure about. So I got to catch more data just to make up for that. Anybody get the error?
18.679.
Tubular. And then I just gotta add and subtract that thing. I never said this was all exciting. All right, there we go. Am I done?
You have to write the conclusion.
Yes. Everybody's favorite step. Oh, I forgot there was a side 2 to this. Oh yeah, I remember this crazy. Oh no, sorry. We are 98% confident that what?
That the interval 59.61 to 96.96 holds the true mean of grades.
Yeah, in this case, since they're grades, there's no real units. This is the one time you can get away without putting units. I mean, you could argue it's like a percent, but it's not real. Holds the true mean grade for all. It doesn't even say. It's funny. True mean grade of this dish, blah blah, of this distribution. Now, I don't know. Again, it's all about if you felt, the more comfortable you felt with the confidence intervals we've done so far, the easier this is going to be to get used to. It's just using a different chart to put a different number here. That's all. That's it. I don't want to take the time to do this, which kind of sucks because I love doing this problem, because what happens is if I have everybody pick a different group of 20 grades and everybody makes their own interval, then I would expect 10% of those intervals to not have the real average in them. Does that make any sense? How confident would anybody be that they caught the real average? 90% confident. So what percent of the intervals would not contain the real mean? I would predict about 10% wouldn't. It normally comes out pretty close. It's kind of cool to see, but we don't have time. I'm already behind, so sorry, problem. These are actual grades, by the way. I just don't remember how far long ago I made this. Anyway, sorry, so I'll stop. All right. I feel like, oh yeah, there is something I sort of forgot. Oh, do I let you guys use notes on quizzes or tests?
No.
This is where I always love it. Somebody's like, yes. And I'm like, oh shit, what have you been doing? But no, of course you can't. But some formulas are notes. So let me remind you guys, we saw this formula before. Remember this formula? Oh shit, hold on. You can't see shit, can you? I don't know why it does that. Okay, there we go. Remember this formula?
Yeah.
This was the definition of z-score. Z-score is the number of standard deviations from the mean to the data point. I know some of you guys are like, you said a bunch of shit there, Jeff, whatever. But a formula is a sentence. And I don't mean like a jail sentence, so stop. What about, look at these two formulas. Does this one look familiar? Yes, Jeff. Does this one look familiar? Maybe. Do you see, when do I use a z-score? When I know this, when I use a t-score, when I know that, holy shit. Sorry. You guys understand what I'm trying to say right now? So I do not let you use notes, but I must let you use formulas, and formulas are notes. They're notes. So what I hate is when somebody says, I have to use this because I don't know the standard deviation. That doesn't make sense. Which standard deviation are you talking about? Does that, you guys get that?
And again, you said it was okay to use the charts.
Oh, you got to, yeah. Dear Lord, I'm not going to make you memorize those suckers. Yeah. Okay. Maybe. So let's do this. Let's take a break. What time is it? Yeah, let's take a break, guys. Let's come back at 2:55. You got more to do, and I want to let us out a little early, just because. Okay.
Could you pull up the last worksheet real quick? I wasn't finished copying down the last part. Yeah, right there. That's perfect. Thank you.
Missed all the other stuff. Damn it. All right. So somebody claims that the mean is 74. I think it's greater. I think it's greater than 74. How would you go check this? What would you, can you get all the math grades? Can you do that? No. What would we do then as statisticians? What do statisticians do? What do you think to check? Take a sample. All right, so let's take a sample. We take a sample of, I don't know, let's say 50. I want you to realize something. What if we get X bar equal to 76? So are you kind of with me? So we took a sample of 50 randomly selected students, and they show us their grade. Are you with me? And so from our sample, we get an average grade of 76. Is that by itself good evidence that the actual overall population average is more than 74? So remember, our claim is the population mean. Do you think that by itself is enough evidence? that is 76 bigger than 74? Yes. So I need you to go past that. That's too basic. So basic. Where did we get that number from? A relatively small sample. 50 is a good size. Do you guys agree with me? It's greater than 30, so that's good. It's got that going for it. But it's still, compared to how many Grossmont students there are, I think there's currently 15,000. We used to be at 20, but you know, things have happened. So relative to that's not a very big size. I really want you to understand this. So by itself, does that show evidence that the actual average is more than 74? No, not yet. Because what's gonna, anytime I take a sample, if the actual average is 74, will my sample mean be 74 every time? Isn't it possible it's 76 just because of random fluctuations? That's possible, right? So, let me see, is everybody with me so far? Do you guys get a feel for this? The fact that that number is bigger than that number don't mean shit, because it's just a little sample. To show evidence that the mean is actually greater than 74 for all Grossmont students in mathematics, I have to get to unusual. So if the mean really is 74, wouldn't we expect our sample mean to be in here somewhere? Right? And normally that's the plus or minus 2. Remember that? Plus or minus 2 standard deviations. All right, so this is where we're finally going to make that a little more refined. It's not always going to be 2, and you'll see why. So if I got a sample here, that's not evidence of anything. It has to be past a certain point. It's got to be out here. Then I go, that's unusual. That would be unusual if 74 was the real average. So what's more likely? It's actually more than 74. So to show evidence that the population is something different than something, my sample must be so far away that it gets into unusual, meaning if the mean really is this, we just did something that's unusual. Well, how do we, what? So let's say this is 2. Let's say this is a z-score of 2. That is where unusual starts for this problem, and which is based on our definition of unusual from before. What would I do to see where my sample falls? All right, this is a great question. I love it. How do I tell if it's up here, down there? Where's 76 go, here or there? I have no idea. So what do I need to do, of course? What do I need to do with what I've discovered? I need to make this into
A z-score to see how far it is from 74.
Yeah, so how do I make this into a z-score? What do I do? Do I have everything I need to turn it into a z-score? Sort of. You got to be a little careful. So can I just do this? Why? I'll tell you this. This is wrong. Why am I wrong?
Because you're subtracting both of them, which are means for a population in a sample.
No, stop. This is the mean of all means. This is my data point. Remember, data points become sample means when I'm taking samples. So that is the formula. The formula for, now be careful, it's not quite the formula, but it's x bar minus the mu divided by the new standard deviation. I didn't change. Didn't I take a sample? Am I now talking about sample means? Aren't I supposed to change standard deviation? Okay. So I really want you guys with me. It's not enough to say 76 is bigger than 74 because it depends on the standard deviation, right? If the standard deviation is 11, is that very different from this? I'm just going to say that. If the standard deviation I'm working with is 11, is 76 very far away from 74? No, it's not even a full step. Do you guys understand? 85 would be a full step up. But is my standard deviation 11? No. So I got to first change that. What's my standard deviation? 11 divided by square root of 50. Whatever the hell that is. 157. 1.57. 1.571. Or probably less than that. 1.562. I'm just making shit up now. Somebody help me out.
1.555.
555? Is that what you said?
Yeah.
Okay.
Yes.
All right. Now, I to be really honest, I am doing a mixture of general and very specific for this explanation. This feels weird because it feels like we're doing a lot of work, but this isn't even a whole problem. This is just a piece of problem. So now I can make the z-score. It'll be 76 minus 74 divided by the right spread. But what does this come out to be? Is this very far away? What is 2 divided by 1.5555? I think it's 1.27.
I got 1.556 for the standard deviation because I rounded the third digit.
Oh, is this 6?
Yeah, and then 2 divided by that was 1.286.
Oh, I got pretty close. So what do you guys think? I really, now look, if I tell the z-score for something is 1.29, is that like really far away? Is that unusual? Is that unusual? Does that mean that that value is unusual? What does this mean? That a mean of 76 is what? What does 1.29 mean?
It's 1.29 standard deviation from
Right, of the mean, right? So did it get into unusual territory?
No.
No, because we said we're working with the old definition, which was it had to be 2 to be considered unusual. It got to right here. And didn't we say, I really want you guys to get this, didn't we say that if this is the correct mean, we would expect our sample to be in here? Didn't our sample show up in there? Does that mean that's the correct mean? Or does that mean we can't say that that's wrong? I love you guys. You guys are like, I don't know, dude.
Can't say it's wrong.
We can't say it's wrong. We can't say it's right. I mean, so this is such a beautiful thing. Let me get down here. Killing my knee. The whole idea is if I want to show this is wrong, my sample has to be unusual, assuming this is right. So what we do is we assume, we go, okay, let's say 74 is the middle. And if I get up here, I'm like, look what I did. You're full of shit. But we only made it to right there. So we were unable to show this is wrong, which is not the same as saying it's right. It's a lot like court. What happens in court? Are you ever found innocent in court? You guys know. You guys have watched enough. What are you found? Guilty or?
Not guilty.
Yes, they never say freaking innocent, do they? They say, we haven't shown you're guilty yet. Don't go too far, right? I mean, that's, no, yes? So really, it's all about, can you find enough evidence that they're guilty, or can you not yet find enough evidence that they're guilty, right? Notice I'm not saying everybody's guilty. It's not, whatever. But it is a cool little analogy with court cases. It's all about finding enough evidence. What does finding enough evidence mean for these kind of problems? Finding a sample that is far away. That would mean that this is more than likely not the right average. All right. So, let's see. What do I want to? All right, let's do this. Let me see if I can back up a little bit. Yeah. Okay. Yeah. Let's do this. Let me see if I can keep that up here. All right. Do you guys remember Or maybe some of you guys do this. Has anybody been to Starbucks recently and actually sat down in Starbucks? I'm still not quite able to do that. I went to a Starbucks and sat outside. That I'll do. But have you ever gone to Starbucks and seen like a group of, let's say 2 old men sitting next to each other, and they're every now and again, they're kind of lightly arguing about something? No? So this, I always see me in the future. I'll be up there with a newspaper and I'm like, Sam, this is crazy. It's fine. What do you mean? It's crazy bullshit. You know, so one old guy has an idea and the other old guy thinks they're wrong. Okay. I love you guys. You're all like, what is this jackass talking about? Old guys in Starbucks. That's our claim. What if we're one of the old guys? What does the other old guy think? So one person thinks this, the other person thinks that's wrong. So what's the opposite of that?
Less than 74.
No,
Not wrong.
no. One guy thinks the mean is greater than 74. What is the opposite of greater than 74?
Less than.
No. Thanks for playing.
Equal to?
Put everything together.
Less than or equal to 74.
Together, don't these cover all numbers? So they're opposites of each other because together they don't overlap and they cover everything. All right, stay with me, stay with me. We have a claim. We have a claim. This is the claim. We have the opposite position. You guys with me? Again, like a court case. He's guilty. He didn't do shit. He's not guilty. He's guilty. So we got 2 positions, and they're opposite positions. Okay, stop. So we have 2 hypotheses. And they're going to be called, all right, you're going to love this. Their technical names are the null hypothesis and the alternate hypothesis. I think on some of my handouts, I'm going to have a 1 here, because some books have a little 1 there. But it's the null. So let me put this down. This is the null hypothesis, and this is the alternate hypothesis, affectionately known as the ho and the ha. So if that offends you, I don't give a shit. So it's the ho's and the ha's. This one, all right, let me see how I want to say this. There's a lot of ways we could have set this up, but the way we decided to set this up is to make this one the one we can show evidence for, and this is the other one. Remind me, did it mean anything if I got in here? Could I say anything definitively if I got in here?
No.
What did it mean if I got something in here? We got in there. What did it mean? It means we couldn't say anything, right? So we really didn't find anything, did we? Where's the areas that deal with evidence? In this case, do you see how this is a 1-tail test? Because I want to be up there. Remember I told you we're coming up on these 1-tail, 2-tail, so you understand better why the T-score chart is the way it is. Do you guys agree with me? That's a 1-tail test. Where's the only place evidence could show up to show this is true? Up there. 1-tail. So when is something 1-tail? When it's got a strictly greater or less than, right? When it's got a greater than, or it's got a less than. It's a 1-tail test. What's a 2-tail test? Not equal to. How can you be not equal to something? You can be bigger or smaller. 2 tails. 2 directions work. Okay, maybe. I understand. This is weird shit. I understand. But it builds on stuff we already know. I can never prove the statement that has an equal sign for this guy. I can only prove the statement that does not have an equal sign. It's up there, down there. So the null will always be the one that's got the equal sign. The alternate will not have the equal sign. So will your claim Will your claim always go here? No. What goes here? The thing that doesn't have an equal sign. So if my claim had an equal sign, it would go here. Okay, I know it. I know I'm driving you crazy. I know. We just started. We've seen one example. So you always look to this guy to see how to draw this, to see where this is. Now let me lay this down right now. Okay. If I get here, what does that mean about somebody who thinks it equals 74? If my sample is here, what does that mean about somebody who thinks it's equal to 74? What does that mean? You can do it. You can do it. I don't know. Do you guys remember what we just said? So did I get into unusual territory if I'm there? Is that unusual territory?
Yes.
Yes. Does that mean it seems that it is 74, or does it mean that it seems that it's more than 74?
More than 74?
Yes, because I really want this to make sense. If the mean really is 74, my sample should have shown up in here, right? Now, is it impossible a sample shows up here and the mean really is this? No. Is it really unlikely? Yes. It would be crazy unlikely, so stay with me. So we can never, statistics can never tell you exactly. What is that? That's weird. It's like a very soft car horn. Somebody, okay. So we call this the rejection region. Because, we see if you guys are cool with this. If my sample gets in there, can't I reject what this guy says? Doesn't this guy say it could be equal to 74?
Yeah.
So if we get a sample that's out here, that means anybody who thinks it is 74 is wrong. That is evidence that they're wrong. It's not proof, but it's evidence.
Is that rejection region the 2 standard deviations and more?
Yeah, it's this whole region right there. So this number is going to depend on the problem. In different circumstances, this could start earlier or later. So let me give you an example of that right now. If you're in a nuclear reactor, not in it, let's be careful. You're not getting irradiated, right? You're not trying to become some mutant or something. You're in a control room and you see the little dial that's got the green and the yellow and the red. Are you going to stay on your ass until that gets into the red? Or if it's in the yellow, are you going to get up and go do something? What do you think? Are you mean like, it's yellow, who cares? I'm going to eat my donuts. Or would you be like me and say, it's in the yellow, this is yeah, I'm going to go see what, which one would you be? You're like, no, I'm going to wait and see if Godzilla comes. And Bryan Cranston, where's Bryan Cranston? No? All right, sorry. Anybody? No? Do you guys understand what I'm saying? So your definition of when the situation becomes unusual is different given the context. So if I'm in a nuclear plant, the minute that needle starts to approach yellow, I am freaking up. I would think. I don't know. I don't know what it's like. Maybe it's not like that. I don't know. But I would. If it was my first day and I'm like, oh, what? It's moving towards yellow. I'm like, oh, shit. Unless you're going, it's still green. Who cares? No, that's not going to be. Yes. So my definition of unusual depends on the circumstances, depends on the possible outcomes if I'm wrong about something. Yes. So each problem could give us a different value here that I have to get past. Okay. Just want to lay that out there right now. So unusual normally means within 2 steps. Does it make sense that I want to change that definition given how bad it is if I'm wrong about something, right? Like a nuclear reactor, it's going to blow up. I think that's bad. Okay, maybe not. So let's do this. Let me show you the example. I think we can start doing the first couple of steps of this. Oh, you're going to love this. I don't know how you feel when I say that. Let me start off by this. When I learned this method, when I learned this procedure, there were 8 steps to what we did. I've gotten it to 5 steps, right? I like to start off that way so that when you see 5 steps, you remember that I said it could have been 8. So deal with the 5. So let's take a look. Hold on. If you look at your canvas, I should have unlocked. Let's see if I did. Oh, Jeff, where are you, dude? Here we go. If you go to, let me become a student. Become a student. You go to unit 9. You see it? Yes, you see it. Hypothesis steps explained. So we're doing hypothesis testing. It sounds painful, I know. Look at all this. Look at all this writing, Jeff. So this is your reference for when you're doing homework. Let me say this right now. We say several things. The way the book does chapter 9 homework is, remember when I said there's 5 steps to a problem? Section 9.1 is like step 1. Section 9.2 is roughly step 2 and 3. Section 9.4 is step 3 and 4. Section 9.5 is when you're finally doing all 5 steps. Are you with me? So section 9.5 is where the full 5 steps problems are. And when you get to section 9.5, I want you to do these steps, not the freaky ass steps the book wants you to do, because the book, again, uses the calculator way too much. Right? And you're like, what's wrong with that, Jeff? It's bad. Okay, it's bad. So let me open this a different way. We're going to do a little bit off of here. Don't worry, we're not going to stay here until 4. Don't freak out. It's already 3:30. It sucks. Too bad for everybody. Let me see if I can open this up. Where are you? Oh no, it's nowhere. Oh, here. Oh, somebody left. Damn it. Let's see. Math 160. Hypothesis testing. All right, screw it, Jeff. Just download it, buddy. It's gonna be okay. Okay. Oh my God, this guy is so slow. Here we go. All right, this is a slightly interesting question. So a researcher believes that the northern Minnesota coyote lives longer in captivity if they're given more room to roam. Now, that kind of makes sense, right? Give an animal some more room, it's probably going to have a happier life, live longer. Probably if you just leave them out in the wild, it's better, but you're with me. The mean lifespan of all coyotes in captivity is this. And the population deviation is that. So isn't it okay that we know those things? If they're in captivity, we probably know everything about them. You with me? So it's fine that we happen to know this stuff. Phil takes a sample of 41 northern Minnesota coyotes that have died in captivity but had more room to roam. Are you guys with me? Somebody left again. Damn. Are you guys kind of with me on this? I made this a little wordy, but I don't know. I made this problem up a million years ago. Finds a mean lifespan of 12.45. Now, isn't the mean for his sample bigger than this mean?
Yes.
Yes.
Can I just stop then and go, well, there you go. He found it. He's done. Yay. It's more, Jeff. It's more. I know you try to be funny right now, Jeff, but it's bigger. We stop and we go home. We already are home. Okay, stop. Why can't I just stop? That is bigger than that. Why can't I just stop?
Because you don't know if it's unusually bigger.
True.
You
And
don't
the-
know it's the sample, Steenie?
The key thing is, yes, this number came from a sample, and I expect samples to deviate. I expect samples to fluctuate. I expect them to have different numbers. So not only does this have to be bigger, it's got to be bigger enough. It's got to be far enough up to be evidence, to show evidence that it really is, for the whole population, really is higher. Okay, maybe. I mean, now listen. If your friend said, I think that M&M's, every M&M bag has more than half of it is blue. You're full of shit. And you open up one bag of M&Ms, and sure enough, more than half of them are blue. Why aren't you just going to go, oh man, you're right? You guys understand that example? Friend says, I think M&M bags have more than, every one of them has more than 50% blue. And you go open up a bag, and sure enough, it's more than half of them are blue. Why don't you just stop and go, yeah, you're right? Because it's just one freaking bag. You could have just happened to pick a bag. Maybe it was the only bag in the entire world where half of it was blue. Is that, yeah, that's possible. Or it's just one of the few where more than half are blue. Are you guys with me? So just a sample by itself cannot prove something by itself. It needs to be really far away. Unexpectedly far. Okay. So can somebody just tell me, what is the claim that's being made?
That the coyote lives longer in captivity.
And now
Like a good and pleasant to him.
when you write the claim down, I need it to be purely mathematical. So let me start it off. The claim is the mean is
Greater than
greater than
10.15.
10.15. I love it. Where'd this number come from?
The sample.
Sample, and that will never show up in the first step because we have a hypothesis before we even take a sample. Are you guys semi with me so far? That's just writing the claim down. That's all we did. Does that claim have an equal sign in it? So you
No.
don't put it here. You put it there. That's all it is. If you write the claim down and it has an equal sign in it, you put it next to the null, right next to the HO. If it doesn't have an equal sign, you put it next to the H1. So here's the one little old guy in the coffee shop. So what's the other little old guy think?
Less than or equal to.
Good. Now, it's always the ha that I can show evidence for. How many tail tests would this be, and where's the tail? Where would I need the sample to show up to show evidence for my ha?
On the right.
Is everybody else with that? So obviously, if the claim is, if the ha is greater, then my sample has to be way up here to show evidence. So outside of usual on this side up, because it's the claim is, and now we see again, that's the one tail. That's why my t-score chart is set up as 1 and 2 tail, because it's related to a 1 tail or a 2 tail hypothesis test. Okay. All right. Let's see if we can do 2 more steps here, because these are old news. Looking through the problem, can you figure out if we can use z-scores, t-scores, or we can't do anything? What tells me I can do something?
If it tells you that it's normally distributed.
If it did that, yeah.
Or
Is
it
it
is greater than 30.
Yeah, n is 41, greater than 30. I like it. Now somebody else tell me, now that we know we can do something, which thing can we do? Can we use z-scores? Do we have to use t-scores? Which one?
Z-score,
Why Z?
because it gives you the population standard deviation.
Yes, population standard deviation is known. In general, if you're like, I don't know, then most likely it's a sample standard deviation, because they would make it really clear, because statisticians were not used to having population information. Like, holy shit, tell everybody. All right, last step for today. We'll finish this up tomorrow, but this is the last step, part C. All right, so we can use Z-scores, we figured out. Look at this weird little dude. Is anybody freaked out about this little dude now that I remembered to warn you about him? What does that mean? Uh-oh, what does that mean? What does alpha mean?
The one tail.
All right, it's the area in the tail. So tell me this, what is the probability? If this really is 10.15 for this group of coyotes, if that really is 10.15, what is the probability that something shows up in the tail? You know it. There's no work to do. You know what it is. 1% chance. So what's more likely that we did, if we find a sample that's in here, what's more likely? We just happened to do something that had a 1% chance of happening, or the mean actually is bigger? What's more likely? There's a 1% chance. Say
The
again.
first thing you said?
Sorry?
The first thing you said?
No, I don't think so. I think I said the first thing was wrong. There's only a 1% chance that we would find a sample mean in here if this is in the right place. So what's more likely is this is in the wrong place. The mean really is bigger. I really want this to make sense. If we do something really unusual, if somebody said, man, there ain't nobody around here taller than 7 foot, and then we go out and we pick 7 people at random and they're taller than 7 foot, all of them, wouldn't that be evidence that the guy was completely wrong? No? Somebody tells you, ain't nobody around here taller than 7 foot, and you go out and you pick 7 people at random, they're all taller than 7 foot, each of them. What do you think about what that guy said? It's full of shit, right? All right, I don't know. So, if we do something that had a 1% chance of happening, given that this is the mean, what's more likely is this is not the mean. That's what's more likely. So that shows evidence for the mean being greater. And we call this the rejection region because if we get in there, we can reject. Yes, we can do this. We can
Oh.
reject the hoe because that's the one. There we go. There we have fun with it. Have fun with it. Because that's the one that has the equal to possibility. So if we get way the shit up here, it looks like the one who thought it was equal to this is wrong. So when I say, all right, so can somebody help me out? You should be able to look, get the Z-score real quick. Look at the T-score chart, of course, right? Alpha's 0.01, one tail, right? 0.01, one tail. Look all the way to the bottom. What do you get?
Could you scroll just like a tiny bit up?
There?
I meant the other way,
What do
sorry.
you mean like, I'm sorry. Is that good?
Yeah, right this one, thank you.
Anybody help me out? What's the Z-score? Alpha?
2.326.
Yes. Cool. 2.326. Yes.
How do you know when to use the Z-score on the T-score chart? And how do you know when to use the Z-score on the Z-score chart? Because I just looked up 0.01 on 0.01 on the Z-score chart and it got 0.5040. Oh no, that is a Z-score. Hang on.
0.01 is not a Z-score. And
Yep.
in fact, if
It's
you want to use the
area.
Z-score chart, you would have to look up 0.99, right?
Okay, so the T-score is just like everything beyond the Z-score chart because it's so much bigger.
The T-score chart is a shortcut for the most commonly used alphas. How many alphas show up on the T-score chart? 5, right? Maybe. 5 columns. You with me? So if alpha was 0.07, can I use the t-score chart? No. I don't see 0.07 on there. I have to go use the z-score chart then and do it the old-fashioned way. I love you guys. Love you guys. So last thing. So what happens if Z star, oh shit, I'm sorry. Z star is what I call it when we calculate the Z-score for our sample. Just because we already have a Z-score here, I call this one Z star because I'm weird. So deal with it. So if Z star, if our sample Z is bigger than 2326, what can we do? If it gets in here, basically, if our sample Z is greater than this, if we get in here, what can we do? Who looks to be wrong? Who can I reject? Who thinks it could be equal to this? Looks like they're wrong. If I get in here, it looks like the one who thought it was in here is wrong, right? I love you guys. Maybe this is bad because this is the end of class and you guys are all like, I heard you say we're going to do something tomorrow, so I'm already turning my brain off. This guy thinks it could be equal. So if I get way the hell out here, I can reject the null. I can support the ha. What did the ha think? It was greater. So if I end up in here, it looks like the ha could be right. It's good evidence the ha's right. I think I'll stop there. I went a little too far. I think you guys are a little burnt out. So that's my mistake. So we will finish this up tomorrow. We will do several examples of this tomorrow. Don't forget the quiz should be open now. So if you wanted to start the quiz, you could. Formulas are on the quiz. Okay. So we'll finish this up tomorrow. Let me know if anybody has a question out there.
I had a question for homework 7.3, number 37.
All right, let me see. There it is. Okay. The one about the weights. Right? Hello?
I think I got a little confused because it said it's a uniform distribution.
Sure enough.
Well,
Yep.
I drew the rectangle.
For part A, I agree.
Okay.
What
For,
does part B do?
oh, it's asking for the normal.
Take a sample of 100, which makes the distribution become
Normal distribution. Okay. That was B, 37B. Okay.
And remember, so you use the formula from a million years ago, the square root of b minus a squared over 12 to get what the original standard deviation is. And then of course, for part B, you've got to divide that by the square root of 100
Mhm.
to get the one for the normal curve you create.
So something can be both uniform and normal.
It can start off looking like anything.
Mhm.
In fact, we've seen problems where it says it has an unknown distribution and then they take a sample of 57. Doesn't that become normal? Don't you start doing z-scores and looking it up?
Mhm.
This problem is hard for a weird reason. It starts off uniform, which we all know what it looks like. We know it's got these formulas and we know the process, but the minute they take a sample greater than 30, it's normal now. For sure. In fact, the sample size could even be less than that because it started off so nice.
So the population is uniform, but the sample is normal.
Stop. All right. Any sample we take could be normal or not. I have no freaking idea. So when I say n greater than 30 means the resultant thing would be normal, I'm talking about if I took every sample possible and plotted them, that would become normal.
But I guess that was more for this question specifically, that the population is uniform and the sample is normal.
Sure, okay, so the population that we're taking samples from is uniform. I love it. Be careful. A sample that I pick from there could look like anything. Again, what ends up being normal is all the possible samples being graphed. So I take a sample and take its sample mean. That is one number. How can that be normal? So if I plot all the possible sample means of all possible samples, they become normal. And I know, I can see it in your face. You're like, I have no idea what this guy's saying. But when I have a problem and they tell me I have a normal curve and the mean is 10 and I take one person, what's probably that's greater than 11, don't we draw the picture? Right? We draw a normal curve, right?
Yeah.
Okay. Isn't the problem taking one person?
Mm-hmm.
Where's that one person in the picture? Well, we're asking, what's the probability that that one person is over here? So what is the picture in that case really of? It's of all people. It's a picture of all people. So in this case, what's the picture of? All groups of 100 people, their means. Or 100 in this case, what was it? Weights in their means. So when I take one sample and I look at all the numbers in my sample, it could be normal, it could be uniform, it could be freaky shit.
But here we know it's normal
No, stop.
because oh, wait.
Any sample I take, all right, and this is a huge thing. This is something I've been going back and forth about whether I want to get into or not. I really want this to make sense. Any sample I take by itself could look like anything. I don't care how big. Take a sample of 18 million. It could look like this. So what am I talking about then when I'm like, I take 18 million, it's definitely going to come out normal. I mean, this one sample, I take its mean. It is a little point. There it is. It's a point on this bigger picture. What is the bigger picture? It's every possible sample, taking their mean and plotting it.
I get that each data point is a sample mean.
Good. So the sample by itself, the sample mean is all the numbers added divided by n, right? So the actual data that I got the mean from could look like anything.
Mm-hmm.
It's when I put them together with all the other means that it becomes normal.
Mm-hmm.
So this one dot is the sample mean, and that one sample mean came from this weird ass looking thing. But since n is greater than 30, if I plotted every sample mean, it's going to look normal.
What is n in this question?
100, right?
Okay. Mean weight of 100. So that is the mean of all the means.
Yes, the mean of all samples of size 100.
So therefore, for B, it is normal.
It is normal, yes, because all the samples would be size greater than 30.
Okay.
I know this is weird, but this is a key. This is interesting because I didn't know if I should bring this up, because the minute I bring it up, I confuse more people than I help. But you thought about this yourself, which is good, but it also really is confusing. But if I just take numbers, if I take 30 numbers, let's say if I take 100 numbers, right? Let's say you have a big old page full of numbers and I take 100 of them. You can't tell me that you believe that would be normal if I distributed them. Couldn't I pick nothing but 8s and 9s? Is that possible from a list from 18 billion numbers if I take 100 of them? Do they have to be normally distributed? No, that's never what I said. If you take every possible sample of 100, does that make sense by itself? Like that one sheet we did where we had the 4 numbers and I took every possible sample of 2. Remember that?
It's like the pizza toppings.
Yes, yeah, it grows quick. So if I had 18 billion numbers and I took every possible sample of 100, that would be an insane amount. And if I plotted every single one of them, they would look like this. They would look very normal, very skinny. So one of these dots is an entire sample condensed to a mean. So what does that one sample look like? It could look like anything. It could be freaky shit.
So then how does that have to do with 337B?
All right, so now listen. What's the distribution for the mean weight of 100? So they mean every mean weight. So what's the distribution for the mean weight of 100?
Okay.
So if I took every mean weight of every group of 100 and plotted them, what would it look like? A normal curve, because n is greater than 30.
Wait, could you say that again?
Yes. If I took every group of 100 and plotted their sample means, it would look normal. Now let me ask you this, because we've done this before. Haven't we seen data, more than 30 data points, that did not look normal? Definitely. All right, look. All right, what if I had this data right here? Oh, what do you got left, Jeff? You can do it. There we go. You with me? So 90% are twos and so forth. And I got 2,000 data points. So 90% of them are twos. Are you with me? Is this sample normal?
No.
Hell no, because the tallest part is on the end. So it would look like this. Wow. And then beep, 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 beep. So what is it I'm talking about? If I took this guy, if I took the average of this sample, and then I did every other possible sample of 2,000, and I took all their averages and I plotted them, they would become normal.
Okay.
So there's two levels to this. There's the what does your sample data look like itself? It could look like anything. But if you plot all the averages of all your samples and your sample sizes are more than 30, they end up looking normal.
I get that. I guess I'm confused on how that's related to the question.
Part B?
Yeah, what is the distribution for the mean weight
Yeah.
of 125? So you're saying that 100 is the mean of all the means, and that
No. So 100 is the number, right? We take 100 weights.
is that the sample size?
Say again, sorry.
Is that the sample size?
Yes.
Okay. And then
It's 100 25-pound lifting weights. So the weird, I don't know if this is involved when they say 25-pound lifting weights. That's are you with it that it says 25 but it's not really 25?
yeah.
From 24 to 26. Okay. So you take 100 of them. You just randomly select 100 of them, right? What would the distribution look like if you did that for every group of 100 and plotted those? So did they really say all of what I just said? No. Do they mean what I just said? Yes. Because you can't have a distribution for one number. Does that make sense?
Yep.
If I said, what would the distribution of the mean age in our class look like? That doesn't make sense. The mean age is one number. So when they say the distribution of the mean weight, they mean for all mean weight of 100. So couldn't one person go take 125-pound weights
Mm-hmm.
and then figure out the average, and then somebody else could go take a different 125-pound weights, right? And then somebody else could go. What if you did every possible sample that you can do? When you plot them, they become normal.
So then how would you, I guess, how would you answer this question then?
Well, part B is easy. The answer is normal because n is greater than 30.
Okay.
And then part C is where you have to change the standard deviation. You draw a normal curve. You make 24.9 into a z-score. You look it up and get the area, right? The minute you know it's normal, you know the process. That makes sense?
Yeah, kind of.
I know you have two levels here. You have the level of concept and then the level of what do I do for this freaking problem, right? So part B is n is greater than 30. So all the weights will become normal, which means for part C, I can make a z-score. I can look it up because the z-score chart works for normal curves.
So what you were saying earlier about how it might not be normal.
If
What
I
was?
take any one sample,
Mhm.
look at the numbers in the sample, they could look like anything.
Sample itself might not be normal, but the sample in combination with every other sample would make it normal.
I got a spider just coming down. Oh gosh, that's really creepy. Oh, fantastic. Sorry. Spider just decided to come from the ceiling. And where is he? Oh well, he's not big. Sorry, say it again.
So I guess now I'm a little lost from what came from earlier. It's the sample itself might not be normal, but the sample in combination with every other possible sample would be normal.
Yeah. So any individual sample. So I really want, there's two levels here. If I look at a sample, look at all the numbers in the sample, it could be freaky as shit.
Mhm.
Now, if I take every sample's mean and I look at all those numbers, those will be normal if n is greater than 30.
And n would be the sample size.
Size of each sample, yes. So if I took a bunch of samples and every sample had 40 things in it,
Yep.
and I take all the averages and plot them, they become normal.
But you don't know how many averages there are. It's just like every average out
Oh,
there.
I see. Yeah, good point. I don't know. It depends on how many things there are and how big my samples are. You take every possible sample of size blank. And how many there are, who knows?
But then that would always be normal, the combination of all of the means.
Yep, that's what central limit theorem says.
Okay.
Yep.
I think I got it. Kind of. Not all of it.
What I really want you to understand is when we do problems in chapter 6 and you drew the picture, you weren't even stopping to think about, well, what is all in this picture? These are all the other individuals that we never said a word about. We're like, what's probably that Sam is taller than 6 foot. So when we draw the picture, what the shit is everything else? It's all the other people, right? Did we say anything about the other people? No, but the problem told me it's normal. That's all I got to know. I don't have to know all the other people. I know it's normal. So when I have a sample size, when I'm taking samples from a big population and I got a greater than 30 sample size, I know it's normal. I don't have to know all the other samples. I know it's normal because the sample sizes are greater than 30.
Didn't you say that just because the sample size is greater than 30 doesn't necessarily mean it's normal?
Be careful. Each sample, when I look at the numbers in a sample, it could look like anything. When I take the averages of every sample and plot them, it's normal if n is greater than 30. I really want this to make sense. So if I condense every sample down to a single number, it's mean. And I plot those, it's normal if n is greater than 30. If I open up any sample and I look at all the data in it, it could look weird as shit. It doesn't have to look normal. But when I condense them to one number and I plot all of those means, all those numbers, they will be normal if n is greater than 30.
So just make sure I got this right. I'm going to say it back to how I understood it. The sample size is 100. The sample itself might not be normal just because the sample size is 100, but in combination with all the other 100 sets of 100 samples, then the mean, or not the mean, the distribution of all the sample means put together is normal.
There you go. Yes.
I will remember that for the next 5 seconds and then be completely confused again.
It's a weird idea, but you understand why I don't necessarily want to bring that up on my own, because bringing that up will cause people to question things they didn't even think they would need to question. So it's always a weird thing for me. Should I bring that up or not? And if it comes up in class, I'll talk about it. Or if somebody like you asked me, I'll talk about it. But I don't know if I should talk about it or not, because I'm like, I don't know if it'll hurt more than it would help. If people realize this, yeah. But it's such an important thing. That's why it's such a weird thing for me to not talk about it, because it's like the fundamental thing. But it's so weird that it kind of is sort of a stumbling block that I don't want to throw in there. So you're thinking more than you need to. And to be honest, you're thinking as much as you should, which is, but that gets you in trouble sometimes, because then these are these deeper concepts that are really difficult to just see. But that's why I like doing that one sheet. You can see every sample. There was a sample that was 1, 1. Was that normal? No, right? Remember that sheet we did together? There was 1, 1, 1, 2, 1, 3. Is the sample 1, 1? Is that normal? Is that normally distributed?
Nope.
No, it's just one thing at 1. Just one bar at 1. It's not normal. But when I took every sample mean, didn't it become roughly normal? Remember that? Didn't it have a little bar and then bigger and then little again?
But that, what the sample size was 2.
Exactly. Yes, sample size was 2, but remember, it started off uniform. It started off pretty already. So the 30 thing is, no matter how ugly it looks to begin with, it becomes normal. If you start off symmetric and uniform is really nice, if you start off nice, you need even less than 30 to become normal enough. It's just that to cover our ass, we always want greater than 30 because sometimes we're not sure what it starts off as. I don't know if that makes any sense.
I think the last part got worse, but that's okay. I'm gonna just stick to what I got.
So real quick, n greater than 30 covers everything.
Mhm.
You could, a smaller sample might work if the original thing looked nice already. In fact, what if it starts off normal? What sample size do I need? 1.
And that's saying that they gave you that it was normal.
If it starts off normal, I could do 1 and be fine. So if it started off almost normal, maybe I could use 5. Sample size of 5 would make it normal enough, right? So if it starts off uniform, maybe 20 would make it become normal enough. Because we did 2 and it already looked pretty good, didn't it? I really want you to understand 30, there's nothing. So 30 just covers everything from pretty to gross, like blah, 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 blah. So if you have something that's already kind of pretty, what I mean by pretty is symmetric and not freaky looking or whatever, then you might need less than 30 to become normal enough. We saw with 2, it became roughly normal. So I don't want that to confuse you. You don't, in every situation, you don't need 30. It's just that 30 covers everybody.
Yep, got that. Okay, thank you.
I need help with the interquartile.
Oh yeah, that's just Q3 minus Q1. So what's range? Isn't range high minus low?
Yeah.
Now think about this. Think about the 5-number summary. If you take one step in, that's the interquartiles.
Yeah.
So like Q0 and Q4, right? The low and the high.
So you're just taking like the high and the low of the quartiles.
Yes, so Q3 minus Q1, that's the interquartile range. Yeah.
Okay. Wow. Okay. All right. Thank you.
Professor,
For my 7.3, oh, go ahead.
sorry, just real quick. It's because I'm doing corrections for 7.1. For number 68C, I'm trying to find the 25th percentile. And I got 34.325, but on the calculator I got 34.313. So I don't know what I did wrong, or
All right, wait a minute. So what'd you get for the Z-score? That's where we
I
start.
got negative 0.67.
Yes.
Yeah. And so I did 36 plus negative 0.67 times 2.5.
Yeah. 10. Yeah. Okay. Okay.
So I got 34.325.
Okay. And your calculator will not necessarily say that because it doesn't round as much as we do. Let me see what answer I got. What number was that again? That was
Number 68C.
chapter 7.
7.1.
All right. Let's see. 34.31. Is that what you got?
34.31. I got that for the calculator.
Interesting. Oh yeah, 325 is the right answer. Yeah.
Oh, okay.
But now that's telling me that some people did not do that the right way. But oh, so that's right. You got the right answer.
Okay. So it's okay if it's a little bit off sometimes on the
It doesn't
calculator.
make sense because we round our z-scores to 2 places. Or we don't even round. It's just that's all we get from the chart, right? It's two decimal places. But z-scores go forever.
Okay.
The chart's just rounded. So anytime you do it using the chart, it's going to be a little different from somebody using the calculator.
Okay, just making sure. All right, thank you.
No, I was just wanting to make sure, because for 7.3, obviously I'm gonna have to do the corrections, but there's not a whole lot of space because I drew out the charts wrong. So I just wanted to make sure it's okay if I rewrote everything
Yeah.
instead of trying to fit everything inside to
Please do.
redo it. All right, thank you so much for staying behind.
See you tomorrow.